Hello, so in this video we're just going to basically do a very quick run through on sort of what ODEs are. I mean, I have done a video on actually what an ODE is, so it might be worth checking that out before you watch this video. But essentially this is just sort of getting into the proper kind of nitty and gritty of introducing the main idea behind ODEs and perhaps some sort of differences between ODEs and perhaps some terminology which we'll be using in this video. And we'll also look at how to solve a particular type of ODE and sort of the whole reason why you would want to watch this series of videos and the reason why you would want to do this module. Okay, so the first thing that we're going to introduce, is this idea of a linear first order ODE. Okay, so what is that? Well, I mean, we're going to talk in more detail about, the order and what it means to be linear. I've already spoken in another video what it means to be an ODE, but remember that an ODE is such that you can take an ordinary derivative. In other words, you can take what I like to call a definite derivative, so dy by dx, or say like the derivative of a function with respect to x. Say if a function is, if the function is dependent on one variable only, and that variable is x, then that means that when you differentiate that function with respect to x, that's called an ordinary derivative. The reason why it's ordinary is, if you like, it's definite. Okay, and I tried to kind of show you with a sign of the opposite case, trying to strengthen this this example. Say if we had now the function, let's call it g to show it's a different function, but this time a function was on x but also on y as well. Well, now we have to choose which derivative we take it with respect to, and that's known as a partial derivative. Okay, so we could differentiate this function with respect to x, or we could differentiate this function with respect to y. So essentially we have to choose which function we different, or which variable we differentiate with respect to with a partial derivative, whereas an ordinary derivative we don't have to choose. Okay, there's only one choice basically, and we call that a definite derivative. Okay, so that's what it means to be an ODE. And basically the idea is, between the linear first order ODEs, it's going to be written something like this. So it'll be dy, say for example, by dt. So say if we have a function y, okay, a function y which is dependent on t. Okay, so y is a function which is dependent on t, and we normally write it like that. So in other words, for example, this could be y equals cos t. Yeah, that's the function dependent on t, or it could be y equals t squared plus 2t. That's another function dependent on t. It's basically, the variable on the right hand side will be t. Okay, so when we differentiate it with respect to t, that's what we can do. And there's only t involved in our function. Okay, so and basically an equation is just basically a differential equation. It's just basically an equation which involves a function, so our function in particular, and its derivatives. So we've got the derivative, okay, and then on the right hand side normally there'll be like the function itself, so let's say y, and also perhaps its variables as well. But that's the only variables that are involved, like the function and function y and t. Okay, that's the only variables involved. So for example, I mean, the thing is, writing it generally is all very well and good if you know what it means, like me. But if you've seen this notation for the first time, you're thinking, what on earth does this mean? So I'm going to show you with an example, for example. Let's say, for example, we have dy by dt equals 4y. Yeah, that is perfectly fine. Equally, we could have dy by dt equals, let's say, 7y plus 3t. That's also fine. Okay, and in general, how we would write this is we get everything involving y on one side, and it's normally on the left hand side. So normally we'd rearrange this to be dy by dt minus 7y equals 3t. So basically we've got everything involving the function y on the left-hand side. We've got the function itself, function y, and also its derivative as well. And normally just kind of for sake of completeness, this doesn't really look that neat in my mind. So what we normally write is we write it like this. So instead of writing dy by dt, we write y dash to show it's the derivative. Okay, so now this looks a little bit more like an equation, more like a familiar equation. It looks a bit like, say for example, it might be a polynomial. So x squared plus or minus 7x, for example, equals 3 whatever. That bit there looks a bit more like a familiar equation. Okay, and that's the reason why I write it. And actually, that's how we come on to solve, particularly with second order ODEs. That's how we would solve something like this. Okay, and likewise we'd rewrite this one as y dash, that's dy by dt bit. okay, minus 4y equals 0. Okay, so that's just kind of getting you into the notation, getting you sort of familiar with this idea. So in general, a linear first order ODE. We're going to come on to what it means to be linear and first order, but essentially we'd write it like this. Well, I can talk briefly about it now. A linear just basically means that we have a coefficient. So here we have a coefficient, okay, and the highest, you know, that it's linear means that basically we're not squaring a function or its derivative. So for example, this wouldn't be, you know, if we took this example here, y dash minus 4y equals 0, this is linear at the moment, okay, because we've got the coefficients, but, you know, this wouldn't be. Say, for example, we have y dash minus 4y squared equals 0. That's not linear because of this squared bit. We're squaring the function y, yeah? So that's non-linear. So basically, you know, if it's linear first order ODE, it basically means that we can write it in a linear way, and it's going to look something like this. This is a general case. But hopefully by showing you with examples, you know, I've strengthened my argument as to what variable means, as to what this actually means. Okay. So now the thing is, it can either be, we can either have constant coefficients in front of our functions. So this here we got a minus 7, that's a constant coefficient, and here we got a minus 4, that's also another constant coefficient. But let's say, for example, we have something like this. So we have dy by dt, or y dash, equals, let's say, or I'll get it all on one side, so minus, let's say, cos t y equals, let's say, 4 sine t, yeah? Right, that is no longer with a constant coefficient. Are you happy? Because this coefficient here in front of the y, maybe if we just rewrite that to look like a y, this coefficient in front of the y is now cos t. Well, as you know, cos t will vary. Yeah, this is a function, if you like, and it will vary. Yeah, equally, we could have written y dash minus ty equals, let's say, e to the sine t, or e to the t, let's just say. Yeah, this is also not constant because t is just t is a function, t is a variable, and variable can change. So essentially, we can have two different types of linear first order ODEs. We can have one with constant derivatives, constant coefficients, and one with variable coefficients. All right, so we can have constant coefficients, okay, and that would look something like this. So it'd be y dash. I'm actually going to write it in the form that I showed you up here. So we have dy by dt, so the derivative on the left-hand side, and just a function involving y and the variable t on the right-hand side. Okay, so I'm going to go back to that, you know, generalized form. So y dash equals, let's say something like ay plus b. Yeah, where a and b are just constants; they're just numbers. Okay, so we've got, you know, we've got the function here y, and we've got the derivative here, and a and b are just constants. Okay, so when we write it like that, we say it's constant coefficients, and we'll look at a method actually in this video as to how we can solve one with constant coefficients. All right, or maybe I'll do it in another video actually, just for kind of completeness. Yeah, I can talk about the terminology in this video. Okay, we can also have one with variable coefficients. Variable coefficients, which looks like this. So again, I'm going to write the derivative on the left-hand side. I'm going to isolate the derivative, all right? And it's going to look something like this. It'll be p of t times y plus q of t, say. Okay, where p of t and q of t are just functions which vary depending on t. Okay, so like I say, you know, this up here, these two up here would be ones with variable coefficients because cos t varies over as we vary t, and t is a function which varies as we vary t as well. So hopefully you can kind of see now what the difference is between constant and variable coefficients. And, you know, we'll look at techniques to solve both of these in future videos. Okay, so now let's talk about this kind of, let's go back to some other terminology. Now you saw up here I was talking about linear first order. What does the order of a differential equation actually mean? So what does the order of a differential equation actually mean? Well, an order is just simply the highest derivative in the equation. All right, so let me just write down a few examples and just show you what I mean. So up to now we've kind of been considering y dash minus, let's say, 4y, or yeah, 4y plus let's say 6 equals 0. Okay, well the highest derivative in this is the first derivative. Okay, it's dy by d. You know, if y is, let's just assume that y is dependent on t. It could be dependent on x. Okay, so y is dependent on some variable. Well, the highest derivative then is this one. Okay, because it's this one here, and it's the first derivative. So therefore, the order of this equation is a first order. Yeah, because that's the highest derivative. Likewise, if we had something like this, y double dash plus cos t y equals 7. Well, what's the highest derivative there? It's this one. It's this one here. It's the second derivative. So therefore, this is a second order equation. Okay, hopefully you're kind of getting the idea. Okay, let's say, for example, if we have something like y4. Now, notice when we write derivatives now, we don't just write that. Okay, I want to show that that is a derivative, that 4 is a derivative, and not just y to the power of 4. So we tend to write it in a bracket just to kind of isolate it, if you like, and just to show that it is actually a derivative. So we've got y to the 4 plus 6y cubed plus 3y, and I'm going to stick to this notation for that, plus 7y equals, let's say, 7e to the t. All right. What's the highest derivative? It's this one. All right, and it's a fourth order. Okay, let's just do it's a fourth derivative, so therefore it's a fourth order. Let's just do one more for completeness. Okay, so let's do y plus ty to the 4 plus 7y cubed equals 7. Well, what's the highest derivative there? Well, it's not that one, it's not that one, it's that one there. It's the fourth derivative, so therefore this is also a fourth order. Okay, so the order is just simply the highest derivative in the equation. Okay, and that's how we describe the order. It's a bit like how we describe the order with an ordinary kind of polynomial. If we had something like x, let's say x cubed plus 4x squared plus, let's say, 7x plus 2 equals 0. Well, what's the highest power? It's 3. So therefore we say that polynomial is third order. You look at the highest power. Well, now, if you like, the powers have just been replaced with something more powerful, which is derivatives. Okay, and so now we're looking at order as being a derivative rather than a power. Okay. I've talked briefly about what it means to be linear. Linear just basically means that we haven't raised the function to any power, and we just write it as what's known as a linear combination, which is just a linear combination. And all that basically means it's a combination of our variables, in this case our functions. Okay, so combination of our functions and its derivatives arranged in a linear way. Yeah, so for example, it is literally just y double dash plus 3y plus, or 3y dash plus 4y, for example, equals 7. Yeah, all it literally means is I've combined all of my functions and their derivatives, so y dash and y double dash, okay, and I've just arranged it in a linear way. So in other words, I put pluses or minuses in between each of them. Okay, I can have each of the function, its derivatives, and I can also have coefficients multiplying at the front if I want to as well. Okay, but I haven't raised my function or their derivatives to any higher power than 1. Right, so so that's what's called linear, and it's combination because you put them all together. Okay. Now, if you're finding it tricky to kind of notice whether something's linear or not, just replace the function, its derivatives, by variables. So let's say, for example, if you have y triple dash plus cos t times y double dash plus 6y dash squared plus ty equals 0. Now, if you're looking at that equation and you're thinking, is that linear or isn't it? Well, just replace the function, its derivatives, by variables. So let's say that y triple dash, let's call that a. Okay, y double dash, let's call that b. Let's call y dash c, and let's call y what's going to be d. Okay, so now if we replace it, what do we end up with? Well, we end up with y triple dash, which remember we called a, plus cos t, and then y double dash, which remember we called b, and then 6y dash, which remember we called, what do we call it, c, and that's squared, so c squared, plus ty, which remember we called d, equals 0. Okay, well hopefully you can see now then, that that clearly isn't linear because we've got a c squared going on. Yeah, if that squared wasn't there, then it would be linear. But because we've got a c squared going on, it's not linear. Okay, so that might help to kind of see what's going on. Now, the next thing we're going to talk about is kind of really central. I mean, I have actually done a video on this, particularly towards the later part of it. You know, I think this is something when I was learning ODEs, I kind of really struggled. I thought, what do we mean by solution? Well, essentially, what we will have is a solution is just basically what we'll get presented with a differential equation, and we're asked to find the solution to that differential equation. All that means is, what is our function that satisfies that equation? Okay, so for example, if we have y double dash plus 6y dash plus 7y equals 7e to the 3t, okay, all it basically is what is that function y that when we put it into this equation, so in other words, when we find y, when we find its first derivative, and when we find its second derivative as well, when we plug it into this equation, yeah, it equals 7e to the 3t. You know, what is that function y? That is the solution to this equation. Okay, and that is essentially what we're trying to find. Okay, now in general, there will be many functions for y. There will be many different functions that will satisfy this equation. Okay, but normally they'll all follow the same. They'll all kind of look the same. So we'll be able to get it in what's known as a general form. All right, but we can actually, you know, there'll be loads and loads of functions that will satisfy this equation. They'll all kind of look the same. So in other words, we can get them in a general form. So we can get our functions in a general form. Okay, but if we're really lucky, we'll be given some data. Okay, and that's normally called initial conditions. Okay, and that's, if you like, just some data which we know satisfies one of the functions that we've got. Okay, and that is the function that we're interested in. So in other words, we get given this differential equation. Okay, we're asked to find what function will satisfy this. Well, we can have many different functions that will satisfy this, but they will all follow some kind of general form. Well, if we're given some initial conditions, so in other words, a particular value for the function at a particular point, then therefore we're able to narrow it down to the exact solution, or what's known as the particular solution. So it could be, for example, so let's say our solution follows the form y equals, I don't know, y equals c e to the 3t. Okay, well, fairly obviously, you know, it's going to be an e to the 3t graph, so it's going to look something like that, right? It's going to look something like that multiplied by some constant. But we're asking, what is that constant there? So this is y against t. This is y against t. Okay, and this is what our solution is doing. Okay, and it could be that one, it could be that one, could be that one, could be that one, could be that one. Yeah, there's loads of different solutions that we can have. Okay, so it could be any one of these graphs. But if we're given some initial conditions, basically, you know, for a particular value of t, let's say t equals 1, we get, I don't know, y equals 4, right? So therefore we know, we can just cross that off, that it's going to be that particular line there that we're interested in. Okay, so that's what the initial condition is all about. It's basically finding what's known as the particular solution, okay, a particular graph, okay? And it's just some general questions that we're going to be asking through this course. There's going to be 3 questions that kind of we're going to be asking over and over again through this course. So the first question is there a solution? Okay, is there a solution that exists? And we call that sometimes the existence. There's a crucial theorem that we're going to introduce in a few videos' time called the existence and the uniqueness theorem. And you know, that is part of showing that actually, can we show that there is a solution which exists? Because if the ODE can't be solved, so in other words, there's no solution to the ODE, then why are we wasting our time trying to solve it? Okay, so the first question that we want to ask is there a solution that actually exists, or do we just save our time and not bother with it? Okay. The next question is there more than one solution? So more than one solution. So how many solutions are there? So more than one solution, and that's sometimes known as the uniqueness. Okay, uniqueness. So in other words, you know, we'll find a solution, normally there's many solutions, right? You know, like in this example up here, there's many different solutions, but we can all kind of reduce all of those solutions down to some general form. So in other words, they'll all kind of look the same, right? Then, you know, we just don't know what some particular values are. So like in this case, we didn't know what this C was, for example, this constant C, okay? But, you know, we could reduce all of the solutions that we found on this graph, say, you know, they all look the same, so therefore we can write them in what's known as a general form, all right? But the problem comes is there more than one general form? So in other words, you know, for example, we could have a general solution that looks like y equals cos t, you know, say if that was one general solution, but then we might also have a solution that, say, looks like this, so y equals sine t. Yeah, well, fairly obviously then, because there's two solutions, we can either have two general solutions, so either have y equals cos t or y equals sine t. Actually, yeah, you know, C, maybe if I put C and A, just to show that we can have constants in front of those as well. Yeah, so basically what we're trying to show is that, is there more than one solution? So say if this was a solution, y equals C cos t, and this was also a solution, y equals A sine t, then fairly obviously there's going to be more than one solution. Okay, so, you know, this is the whole idea behind uniqueness. And there's actually, like I say, there's a theorem that we're going to introduce in a few lectures' time, in a few videos' time, where we'll actually look at a theorem called the existence and uniqueness theorem. All right, and the last one is, okay, if there's a solution which exists, okay, and if it's unique as well, how do we find it? So how do we find our solution? All right, and, you know, for example, we'll look at, is it analytic? Is it analytic? In which case, can we use, you know, some algebraic technique to find it, or do we have to go numeric route? So in other words, do we, you know, numeric is basically just glorified trial and error, okay? But basically, you know, we're going to look at kind of techniques about how we can find a solution. Most of the time, they will be analytic. Okay, that's the solutions that we're going to look for in this course. But sometimes we do have to use numeric approximations, things like that, basically glorified trial and error, and usually we use a computer to find that. Okay?